On April 6th, 2026, 4 astronauts aboard Orion flew farther from Earth than any human in history, shattering a record held since 1970. But that record belonged to Apollo 13, a crew that only set it because they were fighting to survive. Artemis II broke it intentionally, with 50 years of progress behind it, and still did not land on the moon. So what kind of milestone is this, really? The news broke with a wave of celebration. Artemis II had carried its crew farther from Earth than any mission in history. NASA's social channels and press briefings echoed the milestone, with headlines calling it the farthest humans have ever traveled. Numbers were everywhere. The official figure was just over 252,000 miles from home, a range confirmed by NASA's Deep Space Network with pinpoint accuracy, down to a margin of less than 1 mile. For a moment, the agency's voice was confident and almost triumphant, the kind of announcement that turns a technical achievement into a cultural event. The measurement itself is not just a round number. It is a product of relentless tracking, with ground antennas on 3 continents monitoring the Orion spacecraft's every move. Each data point is cross-checked, time-stamped, and plotted against the mission clock. The press releases highlighted the precision, noting that the record was not an estimate but a certified fact, every mile and every kilometer accounted for in the public record. NASA's graphics compare Artemis II's trajectory to the legendary Apollo 13 arc, placing the new peak range front and center. For the public, the moment is electric. The idea that 4 astronauts have now traveled farther than Jim Lovell and his crew did more than half a century ago carries a weight that numbers alone cannot explain. The excitement is real, and for many it feels like the start of something bigger. But as the headlines fade, a question lingers beneath the surface. What does this record actually mean for the future of exploration? 54 years before Artemis II's milestone, Apollo 13's crew found themselves on a trajectory that would define the outer edge of human experience, not by design, but by disaster. On April 13, 1970, an oxygen tank exploded in the service module, instantly transforming a lunar landing into a fight for survival. The phrase, "Houston, we've had a problem," became a touchstone of crisis, echoing through mission control and into households around the world. With the main engine crippled, Jim Lovell, Jack Swigert, and Fred Haise had no choice but to abandon their plans and swing around the moon on a free return path. This emergency route, calculated in minutes by flight directors and executed with the lunar module's small thrusters, flung the spacecraft farther from Earth than any human had ever traveled, over 248,000 miles at the peak. That distance wasn't a badge of progress, but a byproduct of a desperate maneuver, a line drawn by the need to get home alive. Historians often call Apollo 13 a successful failure. The mission's legacy is not a collection of lunar rocks, but the ingenuity and calm that kept 3 men alive against the odds. The record it set became legendary, not because it was planned, but because it was survived. The drama of that moment, of lives hanging in the balance, of engineers improvising solutions in real time, gave the number a weight that transcended measurement. For decades, Apollo 13's arc stood as a symbol of both how far we could go and how close we could come to losing everything. For Artemis II, every mile was carefully measured, not just in distance but in purpose. The mission's 10-day flight plan read more like a checklist than a quest, each phase designed to push the Orion spacecraft's systems to their limits without ever crossing into the unknown for its own sake. A systems analyst on the ground described it as a rehearsal, not a leap. The crew's time in deep space was divided between monitoring the stability of oxygen and carbon dioxide levels in the cabin, and verifying that the environmental control system could keep the air safe and breathable for the entire journey. Sensors tracked every fluctuation, and ground teams watched for even the smallest deviation from the expected 21% oxygen and less than 0.5% carbon dioxide. Navigation was another pillar of the mission. Orion's guidance computers and optical star trackers were tested for accuracy at lunar distances, confirming that the spacecraft could autonomously update its position with a margin of error measured in meters, not kilometers. Communications engineers measured the throughput of the S-band and K-band antennas, logging an average downlink rate of 125 kilobits per second and a steady 1-second round-trip delay, enough for high-definition video, voice, and telemetry, but still a reminder of the growing distance from Earth. Power systems were under constant review. The solar arrays and new small-cell batteries were cycled through repeated charge and discharge routines, with the power bus maintaining a 97% availability rate throughout the mission. Each subsystem, life support, navigation, communications, and power, had to prove itself in the harsh environment beyond low Earth orbit. Artemis II was less about taking risks and more about building confidence, one validated system at a time. In the words of the analyst, it is not about how far you go, but how well you can survive out there, again and again. Distance, for all its drama, is only one measure of progress. Artemis II's record, farthest from Earth, farther than Apollo 13, carries a strange weight because the mission never attempted a landing. The crew remained inside Orion, orbiting the moon, but never drawing closer than a few thousand miles to its surface. There was no descent, no dust, no footsteps, just a silent loop through deep space, then a return home. The record stands, but the practical leap feels unfinished. Radiation remains a stubborn barrier. The Orion capsule carried advanced shielding, yet the dose rates in cislunar space are 3 to 5 times higher than those on the International Space Station. The crew's cumulative exposure stayed well within NASA's limits, but only because the mission was short and solar activity stayed quiet. A longer journey or a solar storm would push these defenses to their edge. No new technology on Artemis II solved this old problem. It only measured and endured it. Autonomy, too, is more theory than reality. When Orion slipped behind the moon, the crew lost contact with Earth for nearly 40 minutes. In that blackout, every system had to function without help. The software is better than it was in Apollo's day. A single fault left unchecked could endanger the mission. Artemis II proved that we can survive isolation for minutes, maybe hours, but not yet for months. The distance record is real, but the risks it reveals are just as real and still unresolved. Inside Orion, the view from 250,000 miles out is both breathtaking and humbling. Commander Jessica Meir described it best. Looking back at the blue marble, you realize how much distance is left to bridge, not just in miles, but in what we're ready to do next. For the Artemis II crew, the journey was never about chasing a number. Every procedure, every system check, every hour spent in deep space was part of a larger strategy, a philosophy built on sustainability, not spectacle. NASA's leadership has made it clear the new era of exploration is about surviving and operating in deep space again and again, not just reaching a record and planting a flag. Policy analysts call it a stepwise approach. Each mission is designed to validate a specific capability, to build trust in the hardware and the people before risking the next leap. Apollo's urgency was fueled by a race. Get there first, worry about the rest later. Artemis moves with a different kind of caution, one that values endurance over drama. This is why Artemis II's distance record feels more like a checkpoint than a finish line. The mission's greatest accomplishment isn't the number on a telemetry screen, it's the proof that humans and machines can work together, reliably, in the harshest environment we've ever faced. The real test isn't how far we can go, but whether we can keep coming back, each time a little stronger, a little more prepared for the unknown that still lies ahead. The next step is clear. Artemis III will aim to put astronauts back on the lunar surface for the first time since 1972. The plan calls for a landing near the moon's south pole, a region never visited by humans, where water ice hides in deep, shadowed craters. This is not just about planting a flag, it is about proving that people can survive and work for days at a time in one of the harshest environments known. The Artemis base camp, still on the drawing board, is envisioned as a permanent foothold with habitats, rovers, and science labs assembled piece by piece over several missions. Each component will be tested in real lunar conditions, far from the safety net of Earth. Beyond the moon, the scale changes completely. A trip to Mars would stretch for months, not days, with no possibility of quick rescue. Communication delays would extend to 20 minutes each way, and the sun's radiation would be relentless. The systems validated during Artemis II and Artemis III, life support, autonomy, and shielding, are only the foundation. Lunar missions serve as a test bed, a place to learn how to adapt, improvise, and endure when Earth is no longer just a radio call away. The roadmap ahead is built on patience and persistence. Each mission is a rehearsal for the next, each landing a lesson for the journey that follows. The distance record stands for now, but the real challenge lies in making deep space not just reachable, but livable. We have crossed a new frontier, yet the milestone feels almost weightless, more symbol than leap. Today our boundaries are set not by distance, but by caution. The true breakthrough will come when we choose to risk, to land, and to reach beyond safety. The next giant step waits.